So I'm going to start the recording from here, and we will talk a little bit first of all about what we're going to do today. So if I can ask you to make sure you leave your microphones on mute throughout the presentation. I think I should have locked it so you can't unmute yourselves, but just in case I haven't. Please ask any questions through the chat box. We will try and pick questions up as we go through to some extent, especially at the end of the section about the approved document F and the changes that came in December 2021, which will be enforced from June this year. And thirdly, this webinar is being recorded, so a recording of this will go up on the YouTube channel, which you can obviously refer people back to if they want to catch up on what they've missed. For those people who are watching on YouTube, these webinars are held live on MESHWORK. MESHWORK is basically a unique network which is run in partnership with Mesh Energy and is designed to bring together developers, architects, and basically anybody who's got an interest in sustainable design or low energy building. And it's a great little platform. No adverts, no hard selling. It's just there really as a collaboration tool. And I can tell you from first-hand experience, there is an awful lot of knowledge that sits in that platform, and people are always wanting to help. So get on there, have a look around, and join up. It's free to join, so there's no joining fee. Just sign your name away. Okay, so what we're going to cover today, we are first of all going to do a little bit about who Mesh Energy are. That's the company I work for and what we do. Then we'll have a quick overview of ventilation in general, and we'll define three key terms about ventilation, which are quite often misunderstood. Then we'll talk about approved document F, which is a guidance document about the building regulations and specifically ventilation. And then we'll talk a little bit more in more detail about some of the changes that came in December 2021 version of approved document F, and some of the key items. And we'll touch on, as part of that, the three types of ventilation that are now shown in ADF. Some of you who are familiar with the older version will know that there were 4 types in the previous version, and it's now reduced to 3. Then we'll talk a little bit about one of those 3 types, which is MVHR, and what it is and how it works, and some of the pros and cons about it. And then we'll get into a little bit more detail about MVHR itself and about the specification and design. So we'll talk about space considerations. So that's generally for the architects who are maybe sort of sketching out a building. How much space do you need to allow for this equipment? Air tightness, ductwork types and layouts, things about filters and filter positions, then a bit about noise, which then does actually refer back to the new approved document because there's some additional information in there about noise, electricity supply and running costs for MVHR, condensate drainage, which is something that people often overlook. And then finally, right at the end, we'll talk a little bit more about some of the key points that hopefully you've picked up through the presentation. And a little piece about Mesh Energy again, about how what I've just talked about then integrates with what we do as services. And finally, there'll be some time for questions. So we've got about an hour. Hopefully the presentation will take up sort of 3/4 of that, and then that will give us a good chunk of time at the end for questions. However, I do have a habit of rambling on during these presentations, so I will endeavour to get us all the way on time so we can go and start our afternoons. So first of all, who are Mesh Energy? So we're a small building consultancy and environmental consultancy based in Farnham in Surrey. We're not a huge company, but we try to punch above our weight. We're independent. That's one of the crucial things. So we're not tied to any particular technology, any particular manufacturers. We're just here to try and provide holistic advice and simplify a quite complicated landscape around building services and engineering and particularly the sort of sustainable elements of that. So moving on to ventilation more generally, the first thing I'm going to do is I'm going to define three things. And the first of those three things is infiltration. So many of you will already be familiar with these three terms and will have a good understanding of them, but they are quite often used in the wrong ways or used interchangeably where they're not actually interchangeable. So infiltration is all about the air that leaks into and out of a building in an uncontrolled manner. So it's not specifically designed to be there. So ventilation is all about air moving in and out of a building, and infiltration is one of the methods that air moves in and out of a building. However, it's not generally been designed into the building. So you wouldn't design infiltration in, it's just a consequence of the building. So it comes in through a wide range of air leakage paths around the building structure. So things like pipe penetrations, gaps in the eaves, little gaps around your windows, anything that you might think of as being a draft is infiltration. So it is the opposite of purpose-provided ventilation. And what we're going to spend most of today talking about is purpose-provided ventilation. So infiltration is generally bad, and we want to minimize it. Now, we're going to caveat that a little bit later on when we're talking about retrofitting, because in some buildings, the purpose-provided ventilation wouldn't actually be sufficient without the infiltration. So we then have to think about, if we're improving the infiltration, about how we then offset that by providing more purpose-provided ventilation. Second one is background ventilation. So background ventilation is the provision of air for breathing, dilution and removal of airborne pollutants, including sort of low-level background odors, control of excess humidity, typically arising from sort of things like bathrooms and utility rooms where you're using hot water and steam is being produced. And it's also for the provision of air for fuel burning appliances. And that's covered off in a separate document from approved document F, which we're going to look at, which is the ventilation side. That particularly is covered off in approved document J. So quite often you will need to refer to approved document F as a starting point, and then also onto approved document J for particular rooms where perhaps you've got a wood burning stove that's not room sealed or something like that. And finally, we're going to look at this idea of purge ventilation. So purge ventilation is not something you're using every day, but it can be, but it is needed, and typically it's there to get rid of things like smells. So that could be sanitary smells, it could be painting, it could be cooking smells, and generally in most houses that is provided by openable windows. So you should not need to open your window, brackets purge ventilation, in order to properly ventilate the house for day-to-day living. You should be able to live in the house quite happily with all the windows shut, and there should be good indoor air quality under most circumstances. And you then use purge ventilation when you have a particular need to provide very high levels of ventilation for short periods. Another piece that's worth mentioning is that there's a new approved document O, which is overheating, and that also may give rise to a requirement for purge ventilation to prevent overheating or to control overheating. And the requirements given in part O may be higher than in approved document F. So you've got three documents you may need to look at for ventilation. So you may need to look at, you'll certainly need to look at approved document F, which is the piece around ventilation in general. Then you may need to look at approved document J, which is for the provision of air for fuel burning appliances. And then you may also need to look at approved document O for the control of overheating through purge ventilation, and part of that is purge ventilation. So what is Approved Document F? Well, Approved Document F is one of a series of documents that's published by the government, and these approved documents show possible routes to compliance with the building regulations. Now, they're not the only route to compliance. However, they are usually the first place that building inspectors and building control officers and engineers would start when looking to demonstrate compliance. Obviously, compliance with the building regulations, which is the law, is obviously mandatory. Now, that's an absolute no-brainer. You must comply with the law. The guidance given in the approved document gives you a very good method of complying with that law. And generally speaking, if you apply with the requirements of the approved documents, you will also comply with the law. But they are not the only means of applying. And of course, Approved Document F is the one that deals with ventilation. So what you may have been familiar with is in the previous versions of Approved Document F, one document dealt with all types of buildings. And to be honest, it was quite a confusing document to read. The new version is much easier to read. It's still not entirely free of a bit of governmental gobbledygook, but it's getting there. It's certainly a lot better than the previous version. And what they've done is they've split it into two volumes. Volume 1, which is about dwellings, is what we're primarily going to discuss today. But there is also Volume 2, which covers all other types of buildings. There are some times when a building which contains rooms that you might think of as being dwellings actually come under Volume 2. Things like hotels, care homes, those kind of buildings, they will often fall into Volume 2 rather than Volume 1. So your normal house is covered by Volume 1, and that's what we're going to concentrate on today. And now within Volume 1, there are 3 types of ventilation that are considered. What was called System 1 in the old version, which is natural ventilation. System 3, which is continuous mechanical and extract ventilation. And finally, System 4, which is mechanical ventilation with heat recovery. And you'll be pleased to know that ventilation sizes have changed for System 1 from the 2010 version. And the ventilation rates for all systems, all 3 systems, 1, 3, and 4 have been updated. The system that's been removed, which was System 2, is for passive stack. So passive stack is no longer mentioned in Approved Document F, Volume 1. So that's gone. So one of the biggest changes, and this is going to be quite an interesting one for architects, is that natural ventilation is now only considered suitable and covered in the guidance for what there's defined as a less airtight dwelling. Now, bearing in mind what we were talking about at the start, about building an airtight dwelling being a good thing, that means that for an awful lot of buildings that we're designing now, we're not going to be able to use natural ventilation and stick within what ADF tells us to do. The other 2 systems, continuous mechanical extract and MVHR, are suitable for all dwellings. So how does the document define this less airtight dwelling? Well, fortunately, it's fairly clear. So a less airtight dwelling is a dwelling which has one of the following. So it's either got a design air permeability of greater than 5 meters cubed per meter squared per hour, which is, pretty middle of the road for most new build now. You'd be pretty disappointed if you weren't designing to better than 5, really, especially if you're trying to build a relatively energy efficient and sustainable home. So that's number one. So for most homes, that's pretty much saying you're going to be looking at MVHR or CMEV. And the second test is that if the as-built air permeability is higher than 3 meters cubed per hour per meter squared at 50 pascals. Now that's obviously based on a test. So if you're designing a building, what they're saying is if you're aiming for 5, you might accidentally end up with something better than 5, and therefore you probably should be looking at MVHR. And with B, it's saying if you tested the building and it comes out better than 3 or better, then you're going to need to have some sort of mechanical ventilation system, so you make sure that the building is properly ventilated. I just see I've got a question, so it's just Catherine saying pop your questions in the chat box. Fantastic. Right, let's move on. Okay, so changes to approved document F in 2021 continued. Well, there's further detail on controls, and there's new requirements for control within the document. There's now guidance on noise, which was a bit lacking in the previous version, and it gives some guidance, although it doesn't have a requirement to test, which is quite interesting. We'll talk about that a bit later on. There's also some detail on air quality measurements. So indoor air quality is obviously, especially with COVID, has been quite a hot topic, but also around pollutants. So things like sort of various chemicals that can be in the air, CO2, various exposure limits as well are all mentioned. So those are, there's now a big table in one of the appendices about what's acceptable and what's not, and how to test for it. There's also updated requirements on humidity and moisture control, and again that's about ensuring there's sufficient ventilation to control humidity and moisture. But that's the prevention of mold and the associated health issues that can come with that. There's also more information about maintenance. There's more information about commissioning. There's more information about handing over systems to clients, especially that's obviously going to affect new build an awful lot, which is interesting. And then the last big section that I wanted to talk about was about retrofit. So clearly we're going to be ending up retrofitting and improving a lot of buildings over the coming years. The UK has some of the poorest housing stock in terms of build quality and energy efficiency in Europe, and we really need to improve that. But one thing that has been noted is that as you improve the energy efficiency of buildings, then it can have a tendency to make the buildings more airtight. And if the building was relying on infiltration as a significant part of its ventilation provision, then as you make the building more airtight, you could end up with a building which has insufficient ventilation. So what the requirement now is that energy efficiency measures carried out on existing dwellings might reduce infiltration and cause the dwelling to become underventilated. Building work should not reduce the ventilation provision of the dwelling unless it can be demonstrated that the ventilation provision after the work is carried out meets the minimum standards requirement of F1, which is basically saying it's got to meet the requirements of the approved document. So if you do reduce the ventilation, or if you do reduce the infiltration, you need to make sure that you're still providing sufficient ventilation to the building. And you could probably demonstrate that through a number of methods, like provision of ventilators, or you could do an air pressure test and show that the infiltration is still correct and provide some ventilators with that. Or it might be that if you build if you really improve the building a lot, you have to provide an MVHR system. And there's some good options around that, either centralized or decentralized MVHR systems could then be used. And then one of the last requirement is a ventilation assessment shall be carried out following the application of energy efficiency measures. And that there's a table which shows what assessment is required under what circumstances, but I'm not going to get into that in too much detail. So what are the three systems that we've talked about already? So let's talk about the first system. So this is probably the system that the vast majority of houses in the UK currently have. It's a simple system. It's relatively well understood, but its application is very mixed. And this is system 1, natural ventilation. Now, in terms of what approved document F refers to as natural ventilation, approved document F says that natural ventilation refers to a ventilation strategy using background ventilators, which is where these are all incoming arrows and outgoing arrows here are, with intermittent extraction ventilation. So that's extraction from wet areas such as kitchens, utility rooms, and bathrooms, which is where these arrows, there we go. So that is, those ventilators only operate when there is a demand for them. So typically that would be maybe your cooker hood in your kitchen and your extract fan in your bathroom. But air is always free to enter and leave the building through these background ventilators. And approved document F gives you the sizes that those ventilators should be. System 3 is very similar to system 1. The main difference being that the fans run continuously rather than running intermittently. So that is the continuous mechanical extract ventilation. So it's that continuous bit which is the difference. So this is now this is possibly the quickest way to move away from system 1 would be to just put a central, well, it could be a decentralized fan unit, but a fan unit that runs all the time, and you would have a system that goes through the entire house, or you could have individual rooms, but it runs all the time. And finally, we have MVHR, and this is what the majority of today's talk is about. And MVHR is the king of ventilation systems as far as domestic goes. And what you're doing is you are mechanically supplying and extracting air from the property. And in the middle, what you have is a heat recovery unit, because your extract air is air that you've paid to warm up in the house, and you're taking that back to the heat recovery unit. You're stripping the heat out of it, and you're exhausting air to the rest of the system. So MVHR stands for mechanical ventilation with heat recovery. And the heat recovery part we'll talk about in a second. Mechanical ventilation is both for supplying air and for extracting air. And that's the definition given in ADF. So how does it actually work? Well, basically you have a heat exchanger. The two air paths never come into physical contact with each other, so there is no mixing of the stale air and the fresh air, but they go through a heat exchanger inside a box, and that box has a couple of fans in it, and those fans can be controlled to deliver the correct amount of extraction and supply. And the idea is that you obviously balance the extraction and the supply together, and that gives you the greatest possible efficiency. So warm extract air is passed through the heat exchanger, and that recovers its heat. And these things are pretty efficient. We're talking, 80% plus of the heat in that outgoing air can be recovered and reused, which can really give you quite a significant energy saving. So how does it work? Well, obviously you've got the fans in there, so it runs on electricity. Typically you'd be looking at a power demand of less than 100 watts. It recovers the waste heat from the exhaust air, and these systems are pretty quiet. There is obviously, as with anything that moves air, there is a certain amount of noise associated with them, but that noise really shouldn't be noticeable in a well-designed system. So if you have a system that sounds like a jet engine, it's not the fault of MVHR, it's the fault of whoever's either designed it or commissioned it or installed it, and they've got something pretty wrong. So 30% loss, 30% reduction in heat loss is potentially possible, and that's pretty realistic on a very airtight house. And what we'll look at in a moment is we'll look at a slide which shows where MVHR is of benefit and where it's not. So how much air do we actually have to supply? Well, you have to meet two criteria in the approved document. So first of all, you have to meet the criteria shown in table 1.3, which is this table here. And that just gives you a supply rate based in litres per second based on the number of bedrooms. So if you have a 4-bedroom house, for example, your air supply rate must be at a very minimum 37 litres per second. Well, 37 litres per second isn't an awful lot for a 4-bedroom house, especially one which has reasonable sized rooms. So there's a second requirement as well, and this is probably the requirement we end up using most of the time as being what sets the minimum, and that is you must have a minimum of 0.3 litres per second per metre squared of gross internal floor area of the house. So that means you literally add up the floor area of every single room in the house, times that by 0.3, and that gives us our floor area. So get my calculator out. So for a 5-bedroom house, where's that crossover going to be? Well, so if we know 43 litres per second, divide that by 0.3, that would mean that for that first requirement to be the predominant one in a 5-bedroom house, we'd have to have a 5-bedroom house that was smaller than 143 1/3 meters squared. Well, I think if you've got a 5-bedroom house squeezed into 143 square meters, that's a pretty small requirement. So what about extract? Well, extract is also given, and it's expressed in terms of the amount of air that you must extract from each particular room. But you've also got the other criteria, which is you should try and meet the supply air. And in most cases, what you end up doing is you end up having to extract slightly more than these minimums. But these are the minimums given in the document. And so for a kitchen, you must extract at least 13 litres per second continuously. In a utility room, that drops down to 8. Same for a bathroom, and for WC at 6. You may also extract from other rooms, of course. Typically, a lot of the sort of larger houses that we work on would have things like pantries, maybe. We tend to extract from pantries. We tend to extract from plant rooms to keep the air in the plant room fairly fresh. We'd also tend to extract from, both supply and extract to home gyms and those kinds of things. So what we do is you have to sum the requirements of the whole house from this table and make sure that and check whether that exceeds what we've calculated for the supply, which is again that floor area times 0.3 or the minimum given in table 1.3. So whichever the higher of those two is what you end up using. Okay, so what are the pros and cons of MVHR? Well, here's a little unit. So let's have a look at some of the benefits. Well, as we've already mentioned, we might well be able to get a saving of around 30% of our total fuel bill. Now, clearly, some of that is going to be offset by the electricity it takes to actually run this MVHR unit. And we'll look at that in a second, as I said. Because it recovers typically around 85–90% of the heat from the extracted air, it gives very, very good, gives it that good efficiency, and it also clearly helps with building heat up and building warmth retention. and it provides controlled, and that's the main thing, controlled building wide ventilation. So one of the things with natural ventilation is that it is affected by the whims of the weather, because if you've got a particularly blustery day and it happens to be blowing at the wall, which has got a lot of the ventilators in, you'll get a greater level of ventilation you will on a still summer's day where those ventilators where the air is not moving through those ventilators through with the action of the wind. So what are the downsides? Well, clearly there's a fair chunk of cost in the installation of such systems. There's ductwork to put in, there's designs to be done, there's space to be left for them. So there is some cost there, and of course, as with any system, there is a maintenance requirement. Any mechanical system is going to require some maintenance, but most of that maintenance is fairly straightforward. It's really changing filters and doing a bit of general spring cleaning. So let's talk about a little bit more in detail about the specification and design of these MVHR systems. Well, the first thing to bear in mind is that air is big. We're talking about liters per second of air moving around the house, and many tens of liters a second of air. So, as I said, for a 143 square meter house, we're going to need 43 liters per second of air going through. So that means for a typical maybe 200 square meter family home, that's a fair amount of air you're moving around. And of course that air needs to go through some sort of pipe or duct, and that duct obviously needs to be sized to take that volume of air at some sort of reasonable velocity, because if you start making the velocity too high, then what happens is it starts getting noisy. So the ductwork can be quite a thing to try and package into a house, especially one where that hasn't been considered early on. So think about where that is going to go, and typically the place you put your ducts is in the ceiling void. You generally want to supply and extract at relatively high levels in the room, and that means you want to have the ceiling void. The obvious space then is to run the ductwork through the ceiling void. You also need to have the plant space. The actual MVHR unit itself has a space requirement, and the other thing to consider is that it's all very well having a nice big ceiling void, but if there's a steel that runs through the middle of it, it can make routing ductwork incredibly difficult. So a ceiling void which isn't a void all the way across is not really much use, because steels and ductwork don't really tend to be great bedfellows. So on larger projects, and by larger projects I'm talking about houses of maybe over sort of 300 square meters domestically, it's probably worth considering using multiple units, because that way you can keep the ductwork size down to a reasonable level, and you can have units dotted about rather than trying to run huge ducts from one central location. Just to note, this picture that was made to make a point, that's not actually a sort of typical size ductwork for a domestic installation. That would be a pretty big commercial installation by the time you're looking at, what's that, probably 400 and probably 800 diameter duct or something. It's that's not typical. So I talked about the effect of air tightness and MVHR, and this graph's taken from a piece of research, and the idea of this research was to look at the cost benefit analysis of MVHR against carbon. So clearly, because MVHR takes energy to run, there is some carbon associated with that, because we use the electricity that we use has a carbon factor, and ventilation is effectively free to run, because all you're doing is really cutting a hole in the building and letting air go in and out of it. So where is that trade-off? Where's the crossover point? Well, all you'll find is the crossover point between when MVHR costs more than it saves is around about the five and a little bit meters squared per hour at 50 pascals, which incidentally you'll note is around about the same value which building regulations, which proof document F now says is where natural ventilation is no longer suitable. So those sit quite nicely, but it's just worth bearing in mind that if you've got a leaky old building, it may well not be a benefit to actually put MVHR in, because it will cost you more to run than the energy it will save, and actually be better off using either spending a bit more time trying to tighten the building up if you want to use an MVHR system, or maybe consider a natural ventilation system instead. So what we do know is that certainly to get to the requirements of RIBA 2030 in terms of indoor air quality and air tightness, you're certainly going to need to use an MVHR system, and it's certainly going to be beneficial on buildings with an air tightness greater than 3, and it will probably reduce CO2 emissions on a building with an air tightness up to 5. And as I say, possible to retrofit, but not ideal on older, leakier buildings, because getting an old leaky building down to better than 5 is pretty tough. So next we're going to look at the 2 major ductwork arrangements. So from each MVHR unit, you will have 2 separate ductwork systems. You'll have one with the supply air in it, and one taking the extract air back to the unit. So one return air, one supply air. And this is the first sort of common arrangement, which is what's called a trunk and branch system. So in a trunk and branch system, you have a main trunk duct, and from that, little branches go off and serve each room. And this is typically the type of arrangement you use when you've got a fair bit of space in your ceiling voids, or if the building is quite long and thin, it can be quite a good option because it sort of suits the geometry of a trunk and branch system. It can be slightly more problematic in a much squarer building, or one where maybe the ceiling void isn't quite so generous, and physically finding the space for this big trunk duct might be challenging. So that's what a trunk and branch system is. Obviously, as you get further away from the MVHR unit, the diameter of that trunk will reduce, and the branches off to each room, the diameter of those or the size of those will depend upon what the air supply requirement is to that particular room. The second type of ductwork arrangement that's quite common is what's called a radial system, and that's much more like a sort of spoke and hub arrangement. So if you imagine a bicycle wheel, this would be the hub of your bicycle wheel, and these would be the spokes going off to the rim of the bicycle wheel. So that's kind of the idea. So from the MVHR unit, you have one big duct that goes to some sort of manifold. Those manifolds are typically flat and wide, and that allows you to hide those in quite a small ceiling void. So if you've got a little drop ceiling over a WC or something, then you could easily hide an extract manifold. And then each room has its own duct that spears off from there. So what's the advantage of that? Well, sometimes they can be a bit quieter because you can reduce the duct velocity in each one of those little branches, because the air is only serving one particular room. It might be a simpler install because you're tending to use semi-rigid ductwork rather than rigid ductwork for these branches. So each of these sort of spokes of the radial wheel is a small duct, and it's semi-rigid, so it's one continuous piece of kind of looks like giant Hoover tube kind of thing. We'll talk about that a bit later on. So it can be a bit simpler to install. And thirdly, there's no potential for what's called crosstalk between rooms, and crosstalk is something you need to manage on a trunk and branch system. And what that means is that effectively, if you imagine one of those big sort of pipe communication systems that you might see on an old submarine or a ship, or maybe you see them in playgrounds sometimes as well. Because there's no direct connection between rooms, everything goes back to the manifold. There's no possibility that if somebody's speaking in one room, that sound can echo through the ductwork and be heard by somebody in an adjacent room. So that's an advantage. The downside of a radial system is that there's clearly a greater total quantity of ductwork, because you've got ducts going off the central point to each room. So especially in sort of longer, thin buildings, you'd have lots and lots of ducts running in parallel with one another. So what are the actual ductwork types? Well, probably the one that that's cheapest and people may be more familiar with from commercial applications is a spiral wound galvanized steel ductwork like this. It's cheap as chips. It's brilliant in commercial applications. It's very suitable for a lot of domestic applications as well, especially where you've got a reasonable ceiling void. And generally that would be what would be used for those sort of primary connections, excuse me, from the MVHR unit outwards. It's relatively inexpensive, as I said, and it's available in lots of diameters. There's flat oval versions of it as well, and it's all built to a standard DW144. So that's the standard to look out for. PVC ductwork. It's available in round and rectangular, and it's there to and it's the rectangular is particularly used where ceiling void space is a bit limited on a trunk and branch system. So that's but it does have higher resistance than an equivalent round system, so that can slightly add to the bills in terms of running costs. Also, you have to be a bit careful about exactly which PVC ductwork you use, because it can be limited for cleaning and things, so you just have to be a bit careful. Next up is the semi-rigid ductwork, which is what's used typically on radial systems. So as I said, this is sort of rigid, it feels a bit like a giant Hoover tube. So if you imagine that tube, you can't crush it easily. You can, but it is flexible within an extent, and for that, it's brilliant. So it allows you to make small offsets and bends and things without having to have joints. But the downside is it can be a bit more resistance, especially in smaller diameters. Typically on a domestic system, that would be about 90 mil external diameter, that duct. So it can be quite a small diameter. And finally, we've got flexible ductwork, and flexible ductwork really should be avoided in most applications on MVHR. It doesn't comply with the regulations when used in long lengths. It does add resistance and it adds potential noise, and it's easy to crush. And obviously, if it was crushed, then it wouldn't allow the air that needs to go through it to go through. We've seen many installations where people have run flexible duct through loft spaces, and then householders ended up bashing it with a box and they've been putting something in the loft, and lo and behold, their ventilation system doesn't work properly anymore. Where it can be used and where it can be quite useful is you can use it for short, and that's less than between sort of 500 mil and 1000 millimeter long connections, sort of at the final point, just to prevent a bit of noise. It can slightly reduce the noise. Okay, so filters and maintenance. So MVHR has one of the benefits we haven't talked about before is the fact that it does actually filter all the air that comes into or out of the property, and that obviously has a benefit from the indoor air quality point of view. It reduces your cleaning bill a little bit, but those filters do eventually those filters do eventually become clogged. So you should really be cleaning those filters every 3 to 6 months. A lot of those filters literally can just be cleaned with a vacuum cleaner. You just pull them out, vacuum them off, pop them back in, and about every 3 to 6 months you should do that. A lot of people don't, and it's one of the biggest causes of poor ventilation on homes with MVHR. And you should replace them annually. Replacement filters cost sort of 30 quid each. They're not hugely expensive, but generally speaking, the householder can do it. It's a pretty simple, straightforward operation. And there's an idea of what you might collect on your filters. So you can see the dust and debris. That's all stuff that otherwise would be coming into or out of your home. So it's a good idea. But there are intake and extract filters, and so generally speaking, you might have a couple of filters. So a pre-filter on your intake, which is quite a coarse G3 filter. Then you'd have something a bit more sort of manly, a bit downstream, a bit finer. So G4 or potentially M5. And then if you've got somebody who has pollen allergies, then you may be able to upgrade those filters to F7, which is a full pollen filter. So when you see those car adverts now talking about pollen filters, all that means is they just put an F7 filter in. It's nothing particularly remarkable. But you can put that on your MVHR system, and that can really help people who have pollen allergies. Obviously, it does rely on them not opening the windows because that will let uncontrolled amounts of pollen into the house. But for some people, it makes a huge difference. It's also important to have an extract filter on the kitchen. So where you've got your extract in the kitchen, and that would generally just be a G3 dust and grease filter, and that just means that any sort of grease or dust that's being generated in the kitchen doesn't end up coating the inside of the extract ductwork. So noise, I mean, it's something that we get asked about an awful lot with MVHR, and the honest answer to the query is, if an MVHR system is noisy, generally speaking, it's down to poor design or poor installation, or poor commissioning. So that's the answer to it. What does ADF say about it? Well, it says the fan unit should be appropriately sized so the fans operating in normal background ventilation mode are not overly noisy. This may require fans to be sized so they do not operate near the maximum capacity when in normal background ventilation mode. Now, just taking that into what we actually do on a day-to-day basis when we're specifying these systems, what we find is that generally speaking, we want to be sizing the unit to be between a sort of background condition between 50 and 60% of full load, which means that you look at the sizing of these units and you think, well, that's quite a big unit, but actually when you plot it out, that could be quite easy to achieve. Okay, and then the final thing about noise is that ADF now gives some noise levels that it thinks you should be achieving. So in bedrooms and living rooms, it's suggesting 30 dB, and in kitchens and bathrooms, so less noise sensitive rooms, so utility rooms probably sort of fall into that category as well. Gyms would obviously be in that category as well. Then about 45 dB. But I would say that a bedroom is probably more sensitive than a living room, so I wouldn't be quite so worried about a living room, a little bit of noise in a living room, but in a bedroom it could become quite noticeable. So what do we do about noise? Well, as I say, we correctly optimize the fan speed and the design of that. We make sure the ductwork sizing is correct. So that means really reducing the velocity in the branch ducts down to about 2 meters per second, and in trunks, the trunk ducts down to around 3 meters a second, and that tends to be enough to minimize noise from the ductwork. And then you can use silencers or attenuators to prevent crosstalk between bedrooms, particularly. Crosstalk between bedrooms is obviously one of the biggest issues. You get somebody snoring in one bedroom, you don't want to be able to hear it in the next door bedroom. And of course, you can put other silencers on to eliminate noise in other sensitive areas. So in terms of electrical supply running costs, it's not really an awful lot to report, really. You just need you're only talking about 100 watts or so. So generally speaking, you just feed the MVHR unit off of a little fuse spur, or potentially a dedicated radial circuit. But you're talking about more than sort of 3-4 amps, absolute maximum. So shouldn't worry about it too much. So it is low running costs. You're not talking about putting a whacking great electrical device on your bill. As that graph that we showed earlier, efficiency gains from the heating system will outweigh the running costs in most relatively airtight modern houses. The fan efficiency, which is something to look for when you're specifying an MVHR system, MVHR unit, is given as a specific fan power, and that is in watts per litres per second, and you should be looking for a value of around 0.7 watts per litre per second. So obviously the size of the house, the bigger the house, then the more watts it's going to draw, because you're going to have to do more, but that gives you a sort of a way of sort of giving a comparable cost, and that altogether equates to less than about £100 a year in electrical cost. Now, obviously, as the price of energy rises, then that will rise as well, but that gives you a sort of order of magnitude. And then finally, on this sort of area, we talk about condensate drainage. So taking warm, damp air, humid air out of a building and then cooling it down. You will then get condensate forming. That condensate needs to be drained away to somewhere. So it is worth considering where that condensate is going to go. So there will be a little condensate drain connection on the bottom of each MVHR unit, and that typically just goes through a waterless trap and then to a drain. Okay, so let's talk about our top 10 considerations. So first things first, please, as architects, please design this stuff in early. It makes life so much easier for everybody further down the line. Consider how the ducts will pass around the structure. That thing I was saying about ceiling voids, you can have a lovely big ceiling void, but if there's a steel halfway through it, then it's not as much use. Insulate the inlet and outlet ducts, and that will pick up on one of the questions I've seen pop up. Allow for condensate drainage. Allow for filter changes, so don't jam your MVHR unit into a place where you're never going to be able to get to it again, because you need to pull those filters out, and those filters are quite long, generally about the same depth as the unit. Allow for system balancing and commissioning. Generally the balancing can be done at the valves in the room, but just make sure that those valves are accessible for balancing. Allow space for the silencers and manifolds that are required. If possible, keep the MVHR system within the thermal envelope of the building, and that's to conserve that hard-won energy you've got back. Maintain the separation between the inlet and outlet ducts. So the ducts that go out of the building, obviously what you don't want to be doing is blowing the exhaust air out and then immediately sucking that same air back into the intake. Ideally a couple of meters apart, but they can go a little bit closer than that. And finally, with inlet ducts and think about where they're, what air they're going to be pulling in. So there's a good case study of a property we've done recently, where the house is being built next to an industrial unit. So one side of the house backs onto this industrial unit. They do some spray painting in that industrial unit. So what we've done is we've taken the inlet for the fresh air all the way all the way around the house, and then out to the very, very far side of the garden. So it's as far away from that potential source of pollution as possible. And then we've put additional filters on it as well, to try and reduce the possibility of that. So this is what Mesh do. So obviously we've been talking about this sort of area here, this M&E package, but we'd like to be involved from really stage one. So as soon as you're starting to sketch things out, then get us involved. The earlier we're involved doing feasibility, giving you some ideas about how you might be able to improve the energy performance of the building, the better. The further down the line you are when you get Mesh involved, then potentially the more expensive and the more rework needs to be done to design that dream energy efficient building. At that stage 4, we can obviously do an awful lot, but it's a lot of the benefits also come further down, and especially at stage 7, people often forget about energy monitoring and air quality monitoring, those kind of things. Optimizing systems and learning from previous projects is where you can make an awful lot of benefit. Well, that brings us through to the end of the presentation. I'm afraid that has taken up the full hour. So I'm going to go through, I can see we've got a few questions coming in already, but if you've got any further questions, please type them into the chat box. So let's have a quick look. So we've got a couple of questions around stoves. So when we design stove systems for homes with MVHR, we tend to have an automatic vent that opens to the room when the door of the stove is opened. But when the door is shut, imbalance in the MVHR system is a potential issue. In practice, it doesn't seem to have been yet, or not at least. But when the door is shut, imbalance. Okay. What measures can be taken to reduce imbalance? It is actually that particular thing is actually picked up in the latest version of ADF. There is actually a whole little section on fuel burning appliances in homes with MVHR or buildings with MVHR. So there is some advice in there, but yeah, generally what we tend to do is say, if you're building a new build home, you really shouldn't need the kind of heating output that you would get from a wood burning stove. So we try first of all to discourage people from putting wood burning stoves in the first place, and then once we've if they really have their heart set on it, we would there's a couple of systems. So a lot of stoves have the ability to have dedicated outside air brought to them through a dedicated duct. There's also a chimney system made by Pujlar, which allows the air intake to come down the sort of through the annulus of the twin, so it becomes a triple wall chimney. So you have your flue in the middle, then an annulus of mineral wool, and then a second annulus around the outside of that, which your intake air can come through. I can't remember the name of the system off the top of my head. The only downside of that is it does mean that the chimney ends up being quite a sort of chunky looking pipe, but that's certainly something worth considering. But yeah, it is an issue combining fuel burning appliances with MVHR and not getting issues of spillage spillage of products of combustion can be an issue. Just working down. Chris asked, would you consider pre-insulated ductwork for MVHR applications? So it is important that you insulate the ducts that go between the intake, so the sort of air coming from the outside to the MVHR unit and the air going back from the MVHR unit to the outside, because otherwise you'll get issues of condensation. Because the ductwork within sort of on the internal part of the system, so the supply and extract air going sort of from the MVHR unit to the rooms, that should be within the thermal envelope of the building. So actually we wouldn't tend to insulate that ductwork, but certainly the ductwork going from the unit to the outside and from the outside to the unit, that absolutely must be insulated with a vapor resistant insulation. So hopefully that answers that question. So Alex, on a retrofit where you're unlikely to get better than 5 air changes now, would you say constant extract is better? Hard to know at the start of a job what air tightness you're going to achieve. Much easier to have an idea on a new build. Absolutely, yeah. So on a retrofit, there's a couple of things you could do. If you're looking to, really targeting improving the air tightness, you could look at some of the small room by room MVHR systems. There's a company called Partel, P-A-R-T-E-L, who make some nice, neat individual room MVHR units, and they're effectively a little fan that goes through the wall, and they have a sort of heat storage element in them, and as the fan reverses direction, I think it's every 4 minutes or something, so it will bring air in, and that air is heated by that heating element you've charged by passing the warm air going out, and they give reasonable efficiency, so that could be worth considering. And then you have several of those dotted around to balance, and then the bathroom ones, they have the ability to be sort of told to just do extract when the bathroom's in use. That kind of also picks up the following question from James. Is it worth considering MVHR to localized areas on a limited refurbishment? Yes, it certainly can be worth looking at that, and again I'm sort of pointing towards that system that Partel make. Lindsay, are there any issues using combined intake exhaust grills as terminations to inlet outlet ducts? Well, what you want to avoid is that issue with short circuiting. So generally speaking, we would suggest putting those inlet and outlet ducts at least a meter apart. I think the absolute minimum you can go to is about 300 mil in the guidance, but we'd certainly suggest you go significantly wider than that. I haven't seen a combined system, but I would assume that they'd have to have something. If you did have something like that, they would have to have something that it deliberately directed the flows away from one another. And then you'd probably want to make sure it was in quite an exposed position so that you didn't get any kind of short circuiting. But yeah, short circuiting is the issue. You don't want to be mixing the intake air with the exhaust air. Yeah, okay. I think that covers off all the questions. Alex just makes the point that there are passive house rated combined intake and outlet that have been used. As I say, I would assume that where they have been used, they must have something in some internal design feature that separates those airflows and make sure they kind of blow in opposite directions, to give you that to ensure that you don't get short circuiting. But it's not something I've personally specified. I would always separate them by at least 500 mil and preferably more. Okay, So thank you very much for your time, everybody, and I look forward to seeing you on another Mesh Energy webinar soon. If you have any further questions, please drop something onto MeshWork, and obviously share the video when it comes out with your colleagues on YouTube. We'd be delighted to get a good number of views on there. It's always nice to know that the effort we put into these is appreciated. Thanks so much for your time, and see you again soon.